Hello, hello, hello. Students, we are starting the detection of the gamma ray source or gamma ray radiation with the help of the GM counter first. Later on, we will do the demonstration of the detection of gamma rays using the another type of detector, that is the scintillator detector. So here we will see the how the radiation is coming and how you are getting the signatures that you are connecting with the gamma ray radiations. While in a case of scintillator detector, you will get to see the spectrum how it is rising with the source. So first of all, I will show you the background radiation, which is everywhere is there. You are also some radiation part you are also generating, and we are also generating, and some granite, some environmental. There is a inbuilt radiation in the environment, so we can also measure that. First we measure the environmental radiation for few seconds, right? Then after that we'll measure the radiation using the sources, and I will also demonstrate the one more important thing, that is the 1 upon R square law. This which is called, if you are keeping far away from the this radiation, that falls using the law 1 upon R square. Means as you are going, supposed to be you are going 2 meter back, the radiation intensity will fall as times of the 1 upon R square. If you are going 4 meters long, then you have to, the intensity will fall 1 upon R square more, then you can do this. So you can calculate the how much radiation will fallen down. So it will fallen down like 1 upon R square curve, right? You could understand that 1 upon R square type of things. So as you are keeping far from there, the radiation will be fallen. So we have to maintain the distance from radiation. So how much distance we have to maintain? This is the experimental which you can see how much far we can sit from the radiation detection, because there supposed to be there is a source. So how far I have to stand over here or here or here? So how I can decide? So this is the law, that is called the 1 upon R square. So first of all, we see the how much counts are coming from the background. I have given this. This is a GM counter. This is the associated electronics for this GM counter, and I have given high voltage to the GM counter to operate this, and now we'll see how much counts are coming as a result of background radiation. So I will start it, and I'm just setting for few seconds. So I'm downing it. This is 0. This is, I'm setting for the 1. So this will gives you the 1 minute. This is a time scale basically. From here, this is, I set the 1 minute. This is a minute scale. So for the 1 minute, how much counts are coming there? So let's see. This is the point here. Something is meshing. I started. It's a very small time, so I have to increase the size. Yeah. So now this is the time 1 minute. After 1 minute, this light will go off. After 1 minute, this light will go off, because I have set the timer for the 1 minute counting. So there is a variable system. So how much you would like to count the detection, this the gamma rays, you can set your timings. So almost in 1 minute you are getting the 14 counts, right? This is my background. Now I will demonstrate how the radiation is falling as you are keeping far away from the detector. Suppose this is my 0, this 19 is my 0, consider this that. Then I will go 5 centimeters far away from this detector. So ma'am, please give me the source of 999 kBq. This is not. Ma'am, this will not work. Ma'am, I did the experiment, it will not work. Please give me the 999 kbq, which I have given to. Here is there. Yeah. Yeah. Where is it?
No, student for this not be allowed.
But it will not work.
So आप just थोड़ा सा कम distance में रखिए.
नहीं जाएगा मैम, मैं कर चुकी हूँ.
But not allowed. For them, it's very high activity. You are okay, so show some other target.
Distance is appropriate. They are seated. अब मुझे 999 का दीजिए, फिर मैं थोड़ी देर का है वो. Where is it? जिहान के पास था ना? जिहान के पास था ना? वो कहाँ है? वो कहाँ है? Black क्यों था? Black क्यों था? So you can put the weaker source. That is appropriate. No, cesium only. Keep there. This is one of the source we have kept. Now you can see how many counts are coming. So I started. So almost more than 14th you are getting. This means here are some activities there. So in 1 minute you are getting 46. Okay. If I am going near to this detector, so just I was kept on the 35. So you can say how much the distance is there. How much distance is there? 16 centimeter. I am going little bit 5 away. Okay, I am putting at the 30. So now see how much the radiation is increasing. So almost 46, right? So let me increase the small. Okay, let me wait for up to the 60 seconds. So I can note it down on the blackboard. So first, what was the distance? 16. How many counts you were getting? 46. Now what is the distance? 11. How many counts you are getting? How much? 83. So this is the 83. Now I change the distance and started again. So what is the distance now? 19 minus this one. How much?
Roughly 6.
6. So I can say some roughly 6. So how much counts will be there? Now you can see how the number of counts are increasing when you are going near to the detector. It is dependent on the distance only.
No, what I mean to say, any radioactive element
Uh-huh.
will be doing the counts as per its half-life, right? Means let's suppose if it's a half-life, or we can say like activity, if its activity is something in Berkeley, that will be independent of anything. But with the distance, we can figure out the inverse square law, and that is the intensity. So if we increase the distance, the intensity is going to reduce. If we are decreasing the distance, the intensity will increase square times, right?
Yes.
So are we measuring intensity over there, or we are measuring the number of counts?
These number of counts are directly proportional to the intensity.
Okay, so like, if we are if we are increasing the distance, it means that a lot many radioactive isotopes are not reaching to the detector.
Reaching to the detector.
Okay, so this is the reason, right? Okay,
Right.
thank you.
Same. Yes, solid angle भी बढ़ रहा है उसके साथ. Yes.
Thank you.
Point source, it's a circular type of the source. It is emitting every direction.
Yeah, so like spherical, it is emitting the
3 pi
radiation
4 pi
in
geometry.
spherical. So by any chance, do we have something where the radiation can be exposed in a, I would say, in a linear manner?
For that, what we use are called collimators.
Okay,
And collimators will basically direct your radiation.
okay.
So it's basically made, gamma rays,
So I hope you are getting like, students, if we are increasing the distance, the radius of the sphere is increasing. So the amount of radiation reaching to that point is decreasing,
Is less.
right?
Yes.
Thank you so much, ma'am, for the
Thank you.
clarity.
The energy will not change, but the intensity will change because of the solid angle. Right. So now these are the 178. This law is also applicable for the light. You can connect directly from the light because the gamma rays are the EM waves as well as your light is EM wave. So follow the same rules, the 1 upon R square law, right? So this is the demonstration of the gamma ray radiation, which is obeying the 1 upon R square law, right? Is there any query? Yes? Counts per seconds, yeah, right? Voltage. This activity, no, this is not giving you the directly Becquerel. It is giving you the counts per second, which is the voltage per across one voltage. You are getting some number of counts per minutes. Yes, this is CPS, not the Becquerel. We have to convert it by multiplying some another units or another constants. So we'll get this C word or Becquerel. The CPS basically Becquerel. CPS basically the 1 CPS is equal to the 1 Becquerel. Next, right? This is the gamma sources. These are the gamma source. So gamma is emitting there. So now we are overing this, switching to the another experiment which is based on the scintillator detector. So now you can correlate it. You are having free data. You can keep your video and you can try to solve it out and see it is following or not, or what are the differences you are getting. And there is some differences will you get here, but later on we will give you the reason why you are getting this, right? So I'm just doing the off power. Yes, beta. Yes, please.
So the 1 by R square law,
Mm-hmm.
is it the same for all mediums?
All BTMs?
Mediums, like,
Yes.
so through air.
The
through-
gamma ray will penetrate any medium.
Okay.
just I am removing this is not forcibly. So this is a scintillator detector, or this is a all in one unit where we are getting the all associated electronics or which is needed to process the pulse which are getting from the scintillator detector. Detector size is only this one. This is the photomultiplier tube, and remaining is the remaining electronics, right? So I have to use one software to operate this detector. That is the Genie, I think. Shutam isko bhi uta. So this is operating. Put off. This software which is Genie developed by the Canberra, this system is supplied by the Canberra, right? So we are operating this and starting this spectrum. So whatever in the background, what you are getting here in the GM counter, all the radiation coming in one form, one voltage. Across the one voltage you are getting the number of pulses. Here you are getting the number of pulses. Here is the MCA. MCA means that energy we have divided into 2048 number of channels. So each channel giving you some sort of amount of energy. Is it clear? This is from background, and I remove this red area. This is nothing for you right now. ROI. I have to clear all ROIs. Yeah.
So can we do one thing like
This is
x-axis?
X-axis is the axis is not a time here.
Energy.
This is the energy.
And y-axis?
The y-axis number of counts. For particular energy, yeah, intensity or number of counts.
So is there any way that we can convert x-axis into time?
Yeah, oscilloscope, we are using the oscilloscope where we are getting the time versus the voltage. Here is the voltage.
Okay.
Here is the voltage. We have to collecting this spectrum with respect to the time. Directly you cannot convert this axis because this is the voltage. This x-axis means the voltage. So we are converting.
So if you increase, is there by any chance you can increase the voltage?
Increase the voltage, yes, I have applied the high voltage, but the limit for that is the MCA is limited 2048.
I have just one thing to tell you here. So you have to think the aim of the experiment. So here aim of the experiment is to find out the radioactive source that is based on the energy. So we need an energy axis with the count axis also. So that is maybe some different type of the experiment where maybe you can convert in different way in the time axis and do that. But here objective of the experiment is different. Just it's the gamma spectrometry where you can find the energy. So this is experiment we are performing with the help of the known sources. And once you complete it and if you have to go for unknown, then you definitely need your x-axis as a energy or channel number and y-axis is a count.
Here we have divided all energy, whatever the energy coming from background or whatever from the sources, we divided into supposed to be 2048 number of graph boxes, similar like that. So we will put the cesium source is giving 662 kV gamma ray energy. If you will put that source, you will find somewhere over here. If I will put the cursor over there, this is gives you the channel number. Here is the 1016 and this is the channel number. You can see passing the cursor, so gives you the channel number idea, and then corresponding that channel number, here is the energy. The lower is the channel, supposed to be here is 295 kV, this channel number, and you are getting the 395 kV, 395 is the channel number and 298 is the energy, right? So something is like that. You can also calibrate this. So if you will put the source, you can see the cesium which is coming, where is it is coming. Cesium peak will start somewhere over here. This 662 kV, something near about to 845. I can calibrate also it. Yeah. This is the rising, right? In parallel, you are looking this another peak. This is the K40. This is the K40 which is present in the environment. We can calibrate it. So something, if I put it some mark, and, calibrate, energy calibration only. So this channel number giving the 662 kV. What is the channel number? I have to take from the cursor, the 662. 662, accept it. Okay. So now you can see this is your 662 kV as per the 854 channel, and here this is correspondingly gamma energy you can calculate. This is somewhere over there. This is the background K40 which is 1.4 MeV, approximately 1.4 MeV. So any query from here, or you would like to see more things? Yeah.
So, on what basis is the highest number of counts being determined?
On what basis the
Highest number of count being determined.
number of intensity, gamma ray, number of gamma rays.
Okay. Yeah.
Here you are asking about the peak, or here you are asking about this reason. Which
Yeah.
reason you are asking? This one?
No, the left one.
That left one because of the background.
The background.
The
And
background.
right one?
Like-
And the right one?
The right one because of the source, that source.
Usually the background radiation count is lesser than the the count
Yeah,
from the
definitely,
radioactive source.
definitely.
But as per the graph what we see here, the peak value is it because of like your start time was different?
Start time is different, or I am recording the different time. If I clear the spectrum, now the background will be less and the peak intensity will be higher. Now you can see. This is the X-ray of the barium, because this source is also giving the barium, and here you can see the lower the peak intensity is higher.
Okay, thank you so much, ma'am.
Yeah,
It's more clear now.
yeah, and it is more clear. Actually, I want to show ki how when you are placing the source, you are getting some energy in presence of background too. Thank you. Then over. We have more time. It may be square law. Yes, I can show you the inverse square law. Okay, the same law which we have did with the GM counter, we can also see over there. So let me stop this spectrum and fix some time. 30 seconds I will put the time, right? Calibrate. Required setting. I am changing the time. So I am collecting the data for 30 seconds only. So 30 seconds, okay. So now you can see this will collect only the 30 seconds, right? That clear the spectrum. Then now supposed to be this is my 0, and I am putting the 5 centimeter far from the detector. Okay? These are 5 centimeter. Now I am starting the spectrum recording. Now you can see I am marking over there, or directly you can say how many counts are there across this peak. Yeah, okay. Ha. At the peak region you can see the more clear spectrum you can see here, and this is the position where you are getting 362 counts or 382 counts. So how many counts you will get in the 30 seconds. So you have to note it down. 499. 495 centimeter, 499 you are getting, right? Then let me increase the distance, the 10 centimeter. Clear the spectrum, now they start. You will also see when I am increasing the distance, this area is also increased. This area will increase. This is the X-ray which is coming from the barrier. Right? How many counts are there? 170. With a 10 centimeter, 171. Now increase the distance, 15 centimeter. In the 15 centimeter, now you can see the clear the spectrum, they start the spectrum. Now sir, you can see that there is no background at all. There will be background. I have to subtract whenever I will analyze for a useful purpose. I have to take the background for the same time and then I will subtract it. There will be. So 102 in 15 seconds. 15 centimeter. And now the 20 centimeter. Start. Thank you. Or this is peak is coming due to photoelectric effect only. There are other events are also participating in this spectrum, which is coming from the same sources, but this is only for the photoelectric effect. How many? 48. Now, you can see the same law you can also verify from using the sodium iodide detector. Right, sir?
Once we can reduce this sample, like we can take it out.
Take it out.
We can check
Background for the 30 seconds. Yeah, sure. I can do need for this further. There is only background, the no sources there. The sources are kept very far.
So even it is possible, like it might not give you any count because there is like if we are detecting only gamma radiation, right? And if this counter is giving only gamma radiation count, and if in our sources in our background there is nothing which can emit gamma radiation, even our background count can be 0 as well, right?
It cannot be 0. Gamma never be 0.
Okay.
There are some backgrounds. I have to subtract. This is the only the background amount.
So I'm just searching for like whether it is going to give in the 30 seconds time period or in 1 minute time period any count.
Yeah,
It will give.
yeah. These are the number of counts.
Acha, I'm just searching there on the top.
They are in the top only. Here the 0 counts at the 6.6 position. The 662 keV. The higher it is in this energy range. Here you can see. Here some gamma ray energy. Some counts. 20, 20, 48, right. In the low energy
Okay.
region, you can getting the background. At this point position where you were getting the this 662 kV, there will not be a count.
Okay. So like yeah, the numbers we have got, the two counts. So that we'll be considering?
12 seconds, miss?
No, no, no. On the top, on the like below the taskbar.
Taskbar, of which this is the time, for that time period we recorded that spectrum.
Yeah, and the count we are getting two there.
To where my cursor is placed. Where is my
Okay.
cursor is placed.
Okay.
If I put my cursor over there, there will be different counts.
Okay. So this cursor, like the placement of your cursor is denoting what? Like where exactly you are getting this 33 counts.
Let me give you the clear picture of the this. Let me down this. Open the PPT. Okay. Let me open some white background. I would like to open some Tavish file, the new. So what you are doing basically, you are having some energy E supposed to be 662 keV, right? When it is interacting with the material, what is happening? It is knocking out the electrons. Apart from the electrons, there are two more phenomena which is generally known, the pair production and the Compton scattering. What happening in the all these three phenomena? Supposed to be this is my nucleus and electrons are revolving around it. This is the most tightly bound electron, which is called the K shell electron. When the gamma ray is passing from this knock out the electron. In the exit channel, I will get one electron here and nothing will be there. This is die out, this gamma ray is die out. So now it is die out, the energy is completely transferred from this electron and the remaining energy in the recoil of this atomic nucleus.
But don't we have like when it is absorbing the energy, we get the absorption spectrum, and when mostly like in many cases the electrons come back, right? And then we get the emission spectrum.
That is a different, this is a low energy phenomenon,
Okay.
what you are telling. I am talking about the gamma ray interactions.
Okay.
It's a high energy phenomenon, the order of the MeV.
So the whole photon will die out.
Whole photon will die out.
Okay.
But your gamma ray source is not a single particle or single energy phenomenon. What will happen when it is interacting with the remaining materials? So there are also some electrons which are revolving around the nucleus, right? Or more electrons. These we considered as a loosely bound electrons. In these loosely bound electrons, gamma ray is coming, interacting, is knocking out the electron, and remaining is losing the energy. Supposed to be here is the energy, and here is the in E dash, and some amount of energy it is losing to eject out some electron. But these electrons are not the tightly bound electrons. These are the loosely bound electrons. So here you are getting some more gamma rays and the electrons with the low energy. So for particular energy here, what will get energy of this electron, and the energy of this electron will be lesser. So in this phenomenon, what will happen? We get a angular distribution. A large amount of energy will get. Not only the single energy, I will get a huge amount E dash, E double dash, triple dash, and so on. So large amount of energy spectrum I will get, which you can see as a result of the Compton scattering. And one more phenomenon which is pair production. I am not explaining much more about the pair production, just I am telling the phenomena which because we have not observed over there. So in pair production, what will happen? In the presence of the nuclear field, there is no role of the electron. The gamma ray is coming in presence of their nuclear force field, whatever the Coulomb interaction, total effective nuclear field. It is breaks into two elements, two particles. These are the electron and the positron. One is the electron, another is the positron. So we have not observed. This is the energy phenomena happen when your initial energy must be the greater than the 1.02 keV. This MeV. So this MeV energy is double amount of the electron energy. The electron rest mass energy of the electron is 511 keV. If you double this, the 1.0 will to come. So if my energy is larger than this amount, this phenomenon will happen. Now we are dealing with these two phenomena. So you can see these two phenomena for particular gamma ray energy. This gives you the idea about what is the gamma ray energy, which is coming out as a result of the photoelectrons. Right? The photoelectrons which you are getting in a spectrum, what you are getting in a spectrum, some X-ray type of thing, some Compton scattering region, and some photopeak. This region, your almost Compton region, where as a result of Compton scattering. That's why you are getting this region when your source is present over there. This is the X-ray of the barium, and here is the photopeak which is coming out as a result of these electrons. Now it is clear picture, and now you can see what is that, how I will collect this electron. Finally, what I am getting my detector, the number of electrons. Now I have to collect these number of electrons and apply some window. If I am collecting some at around 1 volt over there, so some electrons, whatever the energy of the electrons having the 1 volt energy, those are falling in this region, will collect, gives you the number of counts. Okay, over there. Supposed to be this, I divide the 2 volt. So whatever the number of counts appearing in the 2 volt window, you will get some numbers. How many electrons having the 2 volt energy, because you are collecting by applying some electrode or cathode.
So technically, like, a proper amount of voltage is needed.
Yes, the proper amount of voltage is needed, and in this particular, this amount is 2048. This is the number of channels. Number of channels we are divided into 2 MeV. So 2 MeV I divided into 1024. So it's roughly 0.5 keV corresponding to the one channel.
So what you said is that different isotopes will emit different electrons with different energy.
Yes.
So they will correspond to different number of volts.
Right.
And what you have done is that in the channels, you have made that 2048 divided by how many channels you have done. That is the voltage given to each channel, right? Is that
Yes.
so?
This I have to decide by the applying the voltage. When
Depends
I
on the isotope you are choosing, right, ma'am? I mean,
yeah,
just
whatever
energies
my energy range. If I want to measure the 2 volt energy, then I have to divide this 102, sorry, this is a wrong figure.
2204.
Is it 2048 basically?
Correct.
So this is 2K MCA. So 2048 number, I have to divide this 2K. If I would like to measure the 3 MeV, my range up to the 3 MeV, then in that case, I have to divide this 3 MeV energy into the 2048 channel, because this is my limit. My MCA is only the 2K.
So basically, different elements are coming at, they are giving different peaks because their photoelectrons are having different energy. And
Different energies.
so there is basically, you are making a spectrum of different emissions from different isotopes. Am I
Right. If
I
you
got it.
would like to see that, then we can also show
I got
that
it, I got it.
phenomenon. Thank you. All right. So we have to go for the another exercise. So up to now, it's over there. Ma'am, please.
Okay, so you have learned about scintillation process, and you have seen the gamma ray spectrometry with the help of one particular radioisotope, which is nothing but 137 cesium. One of the radioisotope identifier I have already explained to you, and I have shown how to identify or search a radioactive source. And I have shown some background, some sample which is having background activity, and you could identify the isotope, right, the 40 potassium. So here we are going to give you the real experience. So 2 sources are hidden in this room. Now it's your job. I'm going to show you how to operate this RRID, and you have to find the location of the radioactive source and also the name of the radioactive source with this. So here, if you can come a little bit closer, so it will be fine. So here you can see that already I have told you that you have to take this and you have to move around, and you have to see at which place this value is increasing, which is nothing but radiation dose value is increasing. So once the place the radiation dose value will be increasing, that place you have to go for easy ID. And easy ID, we are going for unknown source, so then we have to select unknown and then select. So it will count for 30 seconds, and after 30 seconds it's going to tell you the name of the source, what you are going to find it. Okay, so let's start. So someone can take this one. I'm here to help you. So you take it and just roam around and just tell me where you are going to get higher radiation. So that particular place, maybe, okay, so you can come little bit, you can search anywhere it can be, and wherever you are going to get a more counts, okay. So you see where this value start increasing, you can move. So tell me that particular place, and then we are going to find the source. Yeah, you can give the flyer. Yeah, see, you can go a little bit close to these places. You can come here and go a little bit close and see if you are going to get any identification. You can first move this way, little bit. So come closer like this. Is it increasing? So that means something is here. So here you can see that value is little bit gold glow. So you can see that value is again increasing. You can see that. So go a little bit more further. You can 7, okay? So that means something is here, right? So now what we can go? We can go for easy ID. Then we can, okay, just press it, unknown. Okay, then you can select it. Okay, and see, let it count for, just keep here. Let it count for 30 seconds and see if you are going to get anything or not. So 11 second, 12 second is over. So 30 second total, 21 second is over. Let wait. 24 second, 25, 27, countdown begins. 28, 29, 30. Yes, you are going to potassium 40, but this is because of the natural source, okay? So that means we have to do some further. You have to see if you are going to get anything else here or not. Okay, something you are going to get it. Yes, yes. So that means source is at that particular place as it's vibrating, right? Is vibrating means yes. Go for easy ID, and go for yes unknown. Very good, very good. Select and let's wait. So let it wait for.
Once they identify it, camera पे they can show that.
Yes, 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 definitely. So some more time. 15 seconds is over. 17, 17, 19 seconds, 20 seconds, 21 seconds, 24 seconds, 25 seconds, countdown begins. 27, let's see, we are going to get anything. 28, 29, it's showing unknown, no issue. Let's do once again. This is vibrating, so something is here. So let it count for. Okay, so exit, exit.
This side, they were showing 16, 17.
Okay, so let's wait here
Oh, wow.
and go for easy ID. Unknown. Select. Twenty-one second, 22, 24, 25, 27, 9. Showing unknown, I don't know why. Continue, let's continue. Maybe some more second, so it takes maybe. So activity of the source is very low, so that's why. Yeah, no, because it is showing unknown, so isotope it's not able to identify. So it is giving some more time to identify it. So still it is showing unknown. Continue. 60. No, it's some activities increase, so there are some electronic sources present. So that could be something interfering probably. So let's see that. That if it is not able to, then we have to remove the source. No nuclide fine, no issue. So exactly reset it. EBC ID, unknown, select, let's see.
So should I just get the file down and check? Green.
Here the source activity is quite high. It is 111 kbq. Means per second it's actually giving 1 lakh counts.
So activity is high means dose is high means something is there, but there is a lot of electronics item is present, so that also sometimes can
But actual count
do that,
is
so that
1
could
lakh.
be a problem.
And what about
It's
the other
efficiency
data?
of 5%, 10%, 8% like this. So most of the
Okay, let's
counts
see
are
other place to see. So you can see other place. Let me just
Is it unsafe for human
exit
eyes?
it. So
It's very safe.
so you see other places. So there could be some electronic problem. That's why you see some other places.
So that's why you need to, because it is actually 1 kbq. That is why it's high.
Yes. Can bring here this side. Let's see if anything is there in the drawer or not. So can bring somewhere here. So let's see if anything is here or not. So we are going to get something. So let's see. So go for. You cannot touch whenever you are going to find the radioactive source. You cannot touch anything in your hand. With your hand only, you have to just use the RRIDs to identify it. Okay, so let's see. Sorry.
CO is
Maybe it may be something is
cobalt
open for
57.
contribution. Exactly. Yeah.
Actually cobalt actually.
That we don't know, so you can find it.
Say what is the
Find
atomic
this.
number of cobalt?
So let's see.
But it's an isotope now.
It is isotope 57 cobalt.
Some
What is
problem.
cobalt's?
Cobalt
But
actually,
something is there, but
most
let's
of
see the
cobalt
detail.
stable cobalt is a 59 cobalt.
Okay, so we can see from here also.
we are,
First it can show the
moving
background and
57
then it
cobalt,
can detect.
60
So let's see
cobalt.
if
These
it is
are
able
the,
to do in this case.
But if 59 cobalt,
Huh.
so there's 59 electrons in it now.
59 cobalt means not 59 electrons.
Atomic mass is 59.
Atomic mass is actually.
Okay, so
Atomic mass actually,
number
so
is
atomic number
number
is actually different.
is
Is
27.
27 is the cobalt.
We need to know the mass.
So you can know the what is the number of neutrons because just 57 minus 27. So 30 neutron is there.
30 neutrons.
So number of electron is what?
Okay, so we can just reset it. Maybe that place you can come.
Same.
You can
Number of
come another place and can see.
27.
is it?
Electrons.
I'm
is
just
same-
one more minute it
same
will
number as
take.
protons.
So I think you can just give it to them this FLIR. So another, yeah. So you can give to them. You can just give to them, and we can take this one. Let's see.
Was this identified here?
Okay, so you can
Please
just
take,
check with
once you've
this.
identified, please take this near the camera.
So you can just use this and see whether you are going to get this same or not. So let's take this. He got it right. Okay. No problem. So let's see. We use this one. We see. You can come here if we are going to get anything with this. Yeah, same place, because if anything is problem with that, maybe we can see from here. So we are going to identify it.
Then it is in the background.
So 122nd, it will take some time. Just let's see.
Because we have set the alarm. It is actually alarm. Your place is not very good. And in the range, and that actually, you see this counter, this green means is in the background, but it's put here.
So we are given some time more already, so that if your activity is very low, because the source we are showing here very low active, because you are not trained on this. So you would have higher activity source, you could find very easily. So as so activity is very low, so it takes some time to count it. So let's see. So 122nd. So 1 minute is over. So 1 more minute. Let's
Actually,
wait.
that 30 second, 120 second, we can change it.
Because it's how long?
How you want to, because here data is quite strong. So for 30 second is there.
Can you also change the ranges for background and
Yes,
that as the base limit.
Just after some time it is actually showing the actual limit that we can show on the camera, and after that I will show you how to change the this limit.
It's 40 more minutes time, 30 minutes time more.
We need a password, particular manufacturer password, otherwise you never do things.
20 more minutes, 20 second more.
And show it that you from cover 57. Same.
10 second. Yes, so you can show there in camera, you could identify it. It's manganese 54. So they could identify, so you can show there that in camera you just show that in this way that you could identify it. Yeah, it's not coming. No, just, sorry?
The place of showing is with the vibration.
Yeah, so you have shown it, this 54 manganese. So the place you're vibrating, that's actually source is there. So some reason it could not identify. So you have taken, so if one identifier is not helping you to identify, you can take another identifier, you can do that. So it's a 54 manganese. Okay, so if you have any question, you can let us know. Yes?
So for like identifying radioactive isotopes,
You can
are,
take your camera.
are there any other properties that tell us that they're a radioactive isotope apart from obviously they emit radiation?
So for radioactive isotope, this is the features that is helping you, that it is emitting the radiation. So there could be other property, but you don't need it. So this property itself is sufficient to characterize the isotope from their nature of emission. From their nature of emission. So there could be, because they are, you can talk, if you can discuss in terms of the chemical property, they also have a chemical property like other isotope. But this radioactive emission property is sufficient to identify them from other.
Some could be more dangerous than others. So if we want to identify that they are radioactive isotopes before actually checking for radiation, can we do that?
As they are radioactive isotope, only the radiation will help you to identify them. If you are just only talking about the, based on the radioactivity of that property. Okay, so radiation only is the way to. Any other thing? मैंने चाबी दे दी थी सॉरी मैडम ट्रेनिंग के लिए कभी 99 का वो सोर्स निकालिए मत प्लीज़ तो मतलब रिकमेंडेड नहीं है कोई भी हायर एक्टिविटी सोर्स निकालना स्टूडेंट के लिए